Today, we're exploring the story behind the centripetal acceleration equation, v squared over r. Now, memorization is a crime. I'm here to erase that crime from this equation, because many of you probably already know this equation, but most of you might not know actually why it's there. Like, why is it v squared over r? Why can't it be something else? And it's been tied to the ball. So now, if you spin the rope around, then the ball will follow, making a pseudo-orbital. Kind of like the Earth orbiting around the sun, if you don't understand. So, this will have a radius r. That would be the length of the rope. So, now, let's say that we take 4 points on the circle, where the ball is standing right now, where it's yet to go, where it's yet to go, and where it's gonna go later. So, if it's going clockwise, then V1 is going to be pointing this way, V2 is gonna point this way, V3 is gonna point this way, and V4 is gonna, the arrowhead just disappeared. V4 is gonna point this way. So, now let us assume that delta V is equal to 0. Thus, the change of velocity is equal to 0. Meaning that all of this can be defined under one name, V, we'll call it. But these are only equal in speed. These are definitely not equal in direction. So, even though V1 equals V2 equals V3 equals V4, that's only true in magnitude, but definitely not in direction. You can see that they're pointing in wildly different ways. But let's just take the magnitude for now and define it under a single thing, V. Now, let's say we take a slice of this circle, a very, very small slice. So, this is going to be that slice. This is going to be the radius r. Let's call this angle theta. We'll use a thinner line. And we're going to see the outside as delta L, the change in length. So now, we have quite a few components here. But let's say that we wanted to draw the velocities at different points. As the velocity is always going to be tangential, then the velocity would look like this at the start. We'll call this V1, not to be confused with the V1 we saw at the beginning. And we'll call the other one V2. We'll call the other one V2, not to be confused with the V2 in the beginning either. If you rotate the sector, then these velocity directions will look like this. So this is gonna be V1. That's a little too thick for our liking. V1, V2, and this is gonna be the change in velocity. But the thing is, delta V is gonna be quickly approaching 0. So, delta V is approaching 0. But that also means delta L will be approaching 0. As soon V1 and V2 will have merged together, and there will be no difference if delta V is 0. Thus, we can make an argument, since these are similar triangles, that delta V over V is equal to delta L over R. Delta V times R is equal to delta L times V. Now, let's do some more math. Well, how can we make this a little, I know, more sophisticated? Let's divide both sides by r. Cancel, cancel. Delta V equal V delta L over R, of course. So, now, let's say we divide both sides by delta T. This is very strategic dividing. So, that's going to give us delta V over delta T, and these denominators would, and these denominators would multiply to give us V delta L over R delta T. Oops. Okay. So, now, that gives us delta V over delta T can be rewritten as acceleration. And it's centripetal in this case. And V delta L over R delta T, well, this is just going to give you, this is just going to give you V over R times, let's say, delta L over delta T, and that's going to be equal to velocity. That gives you acceleration is equal to V over R times V, which gives us, well, this is unexpected, which gives us V squared over R. Thank you everybody for watching. I'll see you next time.
Free Science Lab to fall in love with math and science, especially programming.